Good evening, everyone. Welcome to the Network Seminar Series hosted by the Center for Networked Intelligence at the ECE and RBCCPS IASC. It's my pleasure to introduce today's speaker, Professor Saswati Sarkar. She will be speaking on Engineers Without Borders, an engineering approach towards controlling infectious diseases. Professor Sarkar received ME degree from the Electrical Communication Engineering Department, Indian Institute of Science, Bengaluru in 1996 and Ph.D. degree from ECE Department, University of Maryland, College Park in 2000. She joined the Electricals and Systems Engineering Department, University of Pennsylvania, Philadelphia, as an assistant professor in 2000, where she is currently a professor. Her research interests include complex networks, stochastic control, resource allocation, dynamic games, spread and control of infectious diseases, economics of networks, and cybersecurity. She received the Motorola Gold Medal for the Best Master Student at the Division of Electrical Sciences, Indian Institute of Science, and National Science Foundation Faculty Early Career Development Award in 2003. We request all the audience to keep your microphones on silent for the duration of the talk, except while asking questions. Questions can be asked at any time during the talk, either by unmuting and speaking directly or by typing them in the chat box. Over to you, Professor.
Okay, thank you. So before we start, I would just like to share, I want this to be a very interactive, informal talk. So feel free to interrupt me at any time. And Parimal, right? So Parimal?
Yes, please tell me.
Yeah. So I'm sorry. So any of the organizers. So any one of the organizers, if you can kindly monitor the chat box and then alert me that there has been a question, etc., which I may not be noticing, I really appreciate that because I want it to be interactive. I want it to be informal.
Sure, Professor. I can take care of it. Yeah.
Thank you. Okay. So Engineers Without Borders, an engineering approach towards controlling infectious diseases. So this is a joint work with with the doctoral students working with me and some of my colleagues in our department at University of Pennsylvania. They are Rex Ali, Jingran Chen, who has since graduated, Jangyal Kim, who has also graduated, Hesam Nikpe, he has also graduated, and this is also a joint work with my colleague Shireen Shaidi Bidokti. She's a faculty member in our department, and Professor Harvey Rubin. Professor Rubin has a very interesting background for us engineers. He's a faculty member. He's a professor in the medical school of University of Pennsylvania, and he's also a practicing doctor of infectious diseases. So he treats all kinds of infectious diseases like COVID, tuberculosis, etc. That's his experience. So in that sense, his background is very similar to me. So, very similar to me. So in that sense, it was a very interesting collaboration our way, because it was really
Professor.
Yes.
Professor, you're slightly not audible.
I'm not audible.
Yeah.
Okay.
Now
not
it's
sure.
Fine.
Maybe let me move this. Let me hold this closer. Can you hear me now?
Yes, it's audible.
Okay. All right. Thank you. So it is really, so I was saying that the collaboration with Professor Harvey Rubin, who is a professor at the Medical School of University of Pennsylvania and also a practicing doctor of infectious diseases, has been really interesting simply because the difference in the discipline. So, and it's atypical. We do not typically collaborate with doctors. So, and that inspired, in part, the title Engineers Without Borders. I'm not sure if you're familiar with an organization called Doctors Without Borders. So they actually, that organization has doctors serving across physical borders. Like, let us say the doctors in US go and serve in some other country which is ravaged by either war or an natural event, etc. So hence the name Doctors Without Borders. So then obviously here we are not, I mean, this collaboration was local in the sense it was in Philadelphia, but intellectually it was across the borders, significant strong borders between disciplines, and that motivated the title Engineers Without Borders. And so we looked at the spread of actual infectious diseases. So, I mean, not necessarily cyber virus, etc., actual biological virus. And then we looked at it from an engineer's point of view, and we proposed engineering approaches to model and control infectious diseases. Okay, so can we move to the next slide, please? Thank you. Okay. So let us see what an infectious disease really is. So what I would do is I would try to present this infectious diseases, which is a very different discipline in terms of the terminologies which we engineers understand very well. So infection, if you think about it, infectious disease is really a stochastic process evolving over time and space. Okay, something which we are really familiar with. So you have a network of individuals, and there the connections are defined by our social connection. So we have, let us say, if we have physically interacted with someone, then we are connected to that individual, and each individual has a state. Initially, let's consider a very simple state. That means whether he is infected or not. And you can generalize that as well. So whether he is right now susceptible to an infectious disease, or he has been infected, or the stages of infection. That means whether he has just imbibed the infection and then he is not infectious. Then from that, just after just imbibing the infection, from that he moves to the infectious stage, then developing symptoms, and whether the symptoms are serious, it goes to hospitalized, and eventually, or not everyone has to be hospitalized. So from infection, you can also transition directly to recovery or to death. And so we are talking of, so far I talked about four states: SIRD. S for susceptible, I for infected, R for recovered, D for dead. Now in I, you do have different stages. So by the way, the SIRD is very common for almost it occurs across diseases. Where the diseases differ are in the states which are within I. That means, let's say you have an initial right after you have imbibed it, then it is the virus is growing within you, so you're not directly infectious. And then and you haven't developed symptoms. Then after a bit, you become infectious, and you maybe you still haven't shown symptoms, but you are infectious. So that is really the stage at which you propagate the disease the most, simply because you do not know that you are sick, and you don't feel sick, so you interact normally, and but you're infectious. So that's a stage where it's asymptomatic infection occurs. Then from that stage you move on to some symptoms. Then there are different symptoms. Different diseases have different kinds of symptoms. For example, if you look at smallpox, then that will have fever, it will have those eruptions on your body, etc. Or COVID will not have those eruptions, but it will probably have fever, cold, etc. So, and then different durations in the stages of infections, and then different probabilities of recovery, different probabilities of hospitalization, different probabilities of death, etc. So these are really the stages of infection are what different infectious diseases vary. But either way, the state, you can define the state of an individual in terms of SIRD, Or you can define more generally S I1, I2, I3, I4, where I1 to I4, for example, represent different stages of the disease. RD, you can have an hospitalization, you can have quarantine, etc. You can have different various other states. Now, these states of an individual evolve over time. So an individual is initially susceptible, then he imbibes the disease and he moves to that initial stages of infection, and the disease progresses, etc. And then eventually he recovers, or if he's tested, then he tests positive, he is quarantined, and eventually you recover, the individual recovers or dies. So it's really the stochastic process. And if you consider an individual as a node in a network, then the stochastic process is evolving over graph, evolving over space, and it also evolves over time for a given node. So stochastic process evolving over both time and space, we are in general quite familiar with studying such stochastic processes. For example, that was studied quite a bit during, when sensor networks, when everyone was studying sensor networks. So let's say if you're looking at a physical process like temperature, okay, so different, and the temperature evolves both over time and space, and different sensors, their recordings, you can consider those recordings as the states, and the recordings evolve over time and space. So that's the underlying similarity. And let's see. Oh, sorry. I also forgot there are other stages. For example, if there is a vaccine, then whether you are immunized, if someone receives a vaccine, then maybe he has immunity, so he is immunized, etc. And so we have this disease evolving over time, or we have the process evolving over time and the process evolving over space. And we have a network of humans where each human represents a node, and there is a link between two humans. If, for example, if say they are, you could define the link in many ways. That means if they have been in contact in, let us say, last 15 or 20 days, or even let us say in the last, you could consider different time intervals, whether they have been contact in the last hour or in the last day, etc. So and so that defines the ages. So it's the network itself is evolving as humans move, as their contacts evolve. And the disease spreads through, infectious disease spreads through proximity between susceptibles and infectious. So if a susceptible is in contact with an infectious individual, then he will imbibe the disease with a certain probability. Again, please note that this spread process is similar to the spread processes that we as engineers have studied. For example, spread of a message. So that is also, so you have a message and you send it to another, let's say a particular node has a message, and the message actually sent from one node to another. That happens through proximity. If you are considering wireless networks, so the direct communication would happen if the two nodes are within a certain distance of each other. So, and there you could consider infectious as someone who has the message, and susceptible as someone who does not have the message. So the process that is spreading, a contact process, or a process that's spreading through proximity between individuals of different type, is something again we are familiar with. So the whole point of this slide is that I hope I have been able to argue that many of these terminologies or the processes that work in infectious diseases have been studied by engineers in different contexts. Which, what this means is we would probably be able to bring in some of our expertise to tackle actual infectious diseases. Any questions? Okay, then let us move through. So there is a chat. Okay, no. So let us move. Let us move to the next slide, please. Thank you. Okay, then let us talk of control of infectious diseases. Again, we as engineers are familiar with actually control of various stochastic processes. Okay, so, but now Now, the infectious disease is the stochastic process, and we want to control it. So, what are the what are the real control mechanisms for biological infectious diseases? So, when let us say when the disease is just started for COVID, which should be fresh in all our memories. So, initially, when COVID broke, there was no drug to treat it, and probably there is still none. I haven't kept up with the literature, but but at least initially there was no drug, there was no vaccine. The only way you could stop the spread of COVID was by cutting down contact. And that's where the initial response was mass quarantining. So we all, if you remember, there was a lockdown where our all our work, etc., were suspended. That we had to, if at all, we had to work from home, and people were advised not to go in spaces with mass gatherings, etc. So, or they would initially they were advised to stay at home. So that was the mass quarantining phase. And then there is another mechanisms to cut down transmissions in a targeted manner. It's testing and isolation. So soon the first counter which was developed for COVID, and which is typically the case, is you develop a testing strategy where you get some biological samples from an individual, and the biological samples can be different for different individuals. So, but the testing almost always involves acquiring a biological sample from an individual and then test for the presence of virus or even bacteria. So, depending on the disease. And then when that is detected in a substantial amount, then the doctors or the clinicians uh, call for a positive diagnosis. And then they recommend isolation and quarantining. So that is a targeted identification and isolation. These are really the two measures to control a disease initially, at the initial stages of outbreak. Then, as we have seen for COVID, as the disease progresses, the next is, if possible, get a vaccination, get a vaccine. So in that case, and when that is developed, then individuals are vaccinated, and that helps develop an immunity. So that is really the third counter. And then later on, if drugs are developed for treating a disease, which has happened for some diseases, but which has not always happened over history, then that is also a counter. So then let me actually draw some draw analogies with control mechanisms that we are familiar with for the processes that we study as engineers. So you are all familiar with cyber virus, right? Like, let us say, viruses that affect laptops, etc., and which spread through contact. Contact means communication in that case. So then you actually sometimes you test to know whether a device has been infected. So you test the device. So you test the different patterns. You check for certain files and see how they are behaving. So that is the testing phase. And once you know that is infected, then you cut down, you remove it from the network. So that's the isolation. Now, mass quarantining, for example, if there is a widespread attack, and then what do? You cut down, you isolate large parts of the network. So that's like mass quarantining. Vaccinations, well, vaccinations are available for cyber viruses also. The different updates. The updates oftentimes have programs which actually identify and isolate different viruses within systems. Okay, so that you can consider that as a vaccination. And so again, the similar control mechanisms have been studied in the systems that engineers are familiar with, and again, it's possible they have been inspired by actually the counters for biological systems. And it has been but we as engineers have studied those systems. Now, whenever there is a control, we have to consider the cost of the control. And in fact, that is a very well-known concept in actual in well-known concept deployed by doctors. For every medicine that you take, there is a cost and the benefit. Oftentimes there are side effects, and now the side effects may be minor, side effects may be major, but the side effects are the cost, other than of course the cost, the actual monetary cost that you pay for the medicine. So similarly, so that has been studied extensively in medicine. Now, similarly, for controls, for in the processes that we have studied as engineers, and where we have sought to control, we are also familiar. We have also studied the cost of control, cost of controlling, cost of controlling a disease. So, for example, if you look at the spread of cyber virus, so if you are testing, excuse me, that has a certain cost, right? So, and then vaccinations, that may spread of updates, that has a cost. If the device is connected through wireless, so then bandwidth is a precious commodity. When you spread the updates, then the software updates, then you're consuming bandwidth. And if the device is not connected to power, wireless device not connected to power, then you're also consuming battery. So that has a cost. Then mass quarantining obviously has cost. So, so bottom line, and again, in another context, when you're spreading a message, okay, so then what are the controls? You control the, you can control the transmission range, but that has a cost as well. If you choose a large transmission range, then that is going to cause interference with other messages. But the benefit is that this particular message can actually go through. And a large transmission range would also involve a large amount of consumption of a large amount of energy, which would involve the draining the battery of the device concerned. So we are again, we also study spread of, we also study control mechanisms of the costs of different controls. So bottom line, so there is an issue of resource consumption and constraint. So there is a there is a certain amount of a precious resource or a constrained resource, which which should be consumed in limited amount, and the consumption of that resource imposes constraints on the application of control. So for example, for infectious disease, it would be if it's vaccines, so then vaccines have a cost, they have limited availability, at least initially. So then the vaccines had to be the, I mean, the vaccines would have a limited availability. Subject to that, you want to decide the best possible vaccination strategy. Similarly, for testing, that also had limitations initially, because especially if you look at really underdeveloped countries initially, that means I studied about some countries in Africa. So there, during COVID, for several months, close to a year, some countries in Africa did not have any testing facility within the country. So they had to, whenever they collected the biological specimens, they would have to transport to another country to get it tested. So then the testing itself and the test kits were limited. So there was a, in this case, and also the personnel who could administer, who could collect, that would be limited. So these were the costs of testing. And there is a cost of isolation, there is a cost of mass quarantining. What is the cost of mass quarantining? It's a deleterious impact on economic activities, and we had seen that in the wake of COVID worldwide. There was significant economic consequences, because the economic productivity was significantly damaged during the mass quarantinings of COVID. So, and then testing, and then when you are targeting, when you are doing a target testing and you identify individuals who are infected, you isolate them. And then the isolation means they may not be able to conduct their daily activities, they may not be able to participate or their professional responsibilities. For example, for us, we can do a lot of work remotely. So if we are not really very down with symptoms, etc., then we can still continue. Even if we are isolated, we can continue our work. But that is not true with individuals. There are several professions which need physical presence. For example, doctors, then different kind of the entire service industry, let's say cab drivers, then in the hotels, receptionists, cooks, etc., then the cleaners of our roads. So those need physical presence. And so if an individual is isolated, then he would not be able to earn his daily wage because he can't participate in his activity, and he can't be productive, he can't participate in his profession during that time. So that is the cost of isolation. So again, so therefore, bottom line, each control strategy has a cost, and there are constraints. There are some limitations on availability of the control, and which imposes constraints. Okay, so then that's a cost of each control. Then benefits. Well, obviously the benefits are clearer. That means if an individual is vaccinated, then he's not going to fall sick, so he would be in good health. So that's the benefit. Again, if an individual is tested, then we might detect early on that he's infected, which means we may be able to give better medical care. For example, for COVID, you're probably familiar that many people died because of fluctuation of a sudden decrease in oxygen levels. Okay? So sudden decrease of fluctuation in blood pressure. Now, if they were in hospitals, then if there were monitoring, so probably those can sometimes be countered, at least to some extent, and therefore the deaths would be lower. So and that's the benefit of early diagnosis. And also, if an individual is infected and he is diagnosed and quarantined, then he would not be able to spread the disease. So assuming that infection is costly, so the total amount of infection would decrease. So that's the benefit of the control strategy. Okay. So again, and exactly the same for the processes that we have studied. So there are benefits to communication. If we're looking at communication, there are benefits to communication of messages. There are benefits to the controls used to slow down or remove cyber viruses, etc. And whenever there is cost and benefit, we need metrics to quantify the benefits. Okay, so what are the public? So let's look at the public health metrics. Number of cases, the infection count. Again, during COVID, you would find that that would be available daily, every day. You could actually study. I mean, those were available on internet every day. The case count, etc. There would be public health sites which would maintain and make those data available. Number of hospitalizations, then the number of deaths, etc. So these are really the public health metrics. Okay, so now what is the goal for this control? We want to maximize the benefits subject to constraints on the costs, or we can think of a constrained optimization where there are constraints on the specific control, and we should determine the policies, determine or constrain the control policies. And there are benefits. We can consider the benefits as the number of cases, hospitalizations, etc. So we want to maximize the benefits. That means in this case, we want to minimize the number of infection count, minimize the hospitalization, minimize the deaths, subject to cost, subject to constraints on availability of the control. Or there is another way to look at it. That means consider the cost of the control and the benefit. The benefit would be the number of cases, hospitalization, deaths, etc. So the objective function can comprise of both the cost and the benefit. So you want to optimize the objective, you want to optimize the objective function. And depending on some controls will have higher benefits but also higher costs. And so therefore, you have to, if you want to optimize them, maybe they are not the best. For example, an example would be mass quarantining. Like suppose you are able to isolate every individual in principle. Okay, suppose you are able to, I mean, no one is in physical contact with anyone. Of course, for infectious diseases, that's impossible. Otherwise, we can't really continue even minimum amount of functionalities like food production, food delivery, etc. But nonetheless, suppose you could do that. Okay, so then the disease is not going to if you look at the case counts, etc., hospitalization, deaths, eventually or quickly they would drop down. But the cost would be humongous because all the economic activities would stop, and therefore your economy, there would be significant impact on education, significant impact on food production, etc. So maybe that's not viable. So it's always a cost benefit trade off. Okay, so now the terminology, okay, so now we have contextualized, or we have connected diseases to the terminologies which we are familiar with in network science. Okay, so we have talked about similarities. Now let us talk a little bit about the differences. So it's not obviously what we have studied is not exactly what occurs for infectious diseases. There are significant differences as well. So for example, one difference that occurs is this: if you look at vaccination. Okay, so let us say vaccination of uh, consider the propagation of the software patches. Now, in principle, if we are talking of a wireless node, if it has a software patch, it can communicate to another node. Okay, now if it has received the patch. However, that is not true for vaccination. Maybe I as a consumer has received a vaccine, but I can't really replicate the vaccine, not yet, and transmit the vaccine to another individual. So that's an important difference. Okay, and of course there are differences in consequences, differences in cost. Like for example, if we are talking of, let us say, cyber virus. So if we are talking of a machine, so let's say a particular machine, its battery is drained because of the virus, and it becomes dysfunctional. We call that the device has died. So then, but that is definitely not comparable to the death of an actual human being. Because, for example, if you recharge the battery, etc., then it will again become functional. But that's not true for an individual. Death is final for individuals. You can't really resurrect. So, and okay, so that's really one important difference. And let us see what are the other differences. So yeah, so okay, I'll actually, as we progress, I'll just share some other differences that we come across. So any questions at this point? Okay, then let's move on to the next slide. All right, let's start with the first counter, testing for infectious diseases. Okay, so now I'm going to get into the specifics of testing strategy and see how we as engineers could contribute through illustration of our work. Okay, next slide, please. Okay, so what testing tells us. So the disease, we are talking of infectious diseases which spreads through contact. Okay, so and therefore, since it spreads through contact, there is a spatio-temporal correlation amongst the disease states of nodes. Okay, so for example, if a node, let us just consider that a very simple state, I, or I means infected, or susceptible, S. So the state, if a node is infected, if you know that a node is infected at time t, now that's going to tell you something about the state of that node in time t plus 1, or it's not going to give you an exact prediction, but or it's not going to give you an exact outcome, but you may be able to predict with a certain amount of success. So state of a node, the infection state of a node at a time t is informative about the state of the same node at a future time, and therefore also at a past time. Okay, so if you know the current state, then you may be able to infer about the previous states. And it is also informative about states of neighbors. So let us say an individual is found to be infected. Okay, then there is a higher probability that the members in his household are infected because they have been in constant contact with the same individuals, or members in his workplace are infected, or maybe the members in his apartment building are infected. But of course the probabilities change, right? That means if an individual is given that an individual is infected, probability of infection in his household is probably the highest because the contact is most significant, or the contacts happen over longer duration. Then maybe then probability of infection in his workplace, among his direct colleagues. And then the next could be probability of infection in his apartment building, okay, or in his social community. Or maybe, and somewhat less would be the probability of infection of individuals who he has casually encountered. Like, let us say I have gone to a shop, another individual has also come to a shop. Then if that individual, if we come at the same time, if that individual is infected, then there is a chance that I may have imbibed the disease. But the probability is probably low, given that the duration of the contact is also low. But so bottom line, the state of a node regarding infection is informative about the state of the same node at different times, and state of neighbors again at different times. And the correlations depend on the connection rates, the contact duration, the frequency of contacts, etc. So then testing of an individual for a disease has a dual role. So when an individual is tested, if he is found to be positive, then he is detected, or if he is detected to be positive, then he is isolated. Okay, so the role of testing is to detect those who are infected and isolate them. But it has also another role, which is predicting the evolution of the disease in neighborhoods of tested nodes. So testing, for example, testing can also be purely for the purpose of gathering information, because you may just want to study how the disease is evolving over time and space. And that's where states, because of the correlation across nodes, that's what you can learn by testing an individual or testing different individuals. Okay, so this is really the dual role of testing: detection and isolation of individuals, and predicting the evolution of disease in neighborhoods. Any questions? Okay, let's move on to the next slide. Okay, so I'm actually running short on time, I think. All right, so let me just speed up a little bit. So exploitation versus exploration. If those of you who have studied machine learning are probably familiar with this terminology, exploitation versus exploration. We found that this phenomenon occurs also for infectious diseases. Okay, so now a disease spreads through symptomatic contact and also through asymptomatic contact. That means an individual may be infectious, but he may not have any symptoms at all, either now or ever, but he may still be spreading the disease. So the disease spreads through both symptomatic and asymptomatic contacts. Okay, so now when you test an individual for an infectious disease, the test typically only exploits available knowledge. Let's take an example. What is the most common testing strategy? Contact tracing. Okay, so then that means an individual is found to be positive, then the individuals who have been in contact with the individual who has tested positive are tested. Okay, that's contact tracing. Then what are you doing here? You are actually exploiting available knowledge. So you have acquired some information by testing an individual. You are using that information to decide who should be tested next. Okay, that means testing the neighbors, etc. Now, the obvious pitfall of this is it does not venture to untested regions. So maybe the disease is silently growing in a community in which no one has been diagnosed yet. So, but because we are only testing individuals who are symptomatic or who have been in contact with those who have been tested positive, we don't test any individual in that community. So then there is a silent spread, and suddenly a large cluster of infected nodes may appear. Okay, so therefore, so what this tells us is just exploiting available knowledge may not be adequate. We may need to explore the unknown, test nodes even if they are far off from infected nodes, and even if it is suboptimal in the immediate aftermath, because maybe the probability that you find someone infected in a distant locality is low, but to prevent but considering the gains in the long run, you'd still want to do it. So then, and we all know for any testing policy, there are test budgets, right? The number of tests that you would use for a particular region, etc. So we could actually budget the tests amongst exploration and exploitation. And then there is a trade-off between exploitation of knowledge and exploration of the unknown. So there is a, let's say there is a finite number of, there is a given number of tests that you can do at a given time. So then you want to use a certain number to exploit, that means certain number to test the individuals who are most likely to be infected, and the rest to explode the unknown. Okay, so that's the trade-off. How many should you use to exploit available knowledge? How many should you use to explode the unknown? Okay, so, okay, any questions? Okay, let's go on to the next slide. All right, so then again, if you're familiar with machine learning, you have probably come across multi-armed bandit. So there, we are the machine learning community. The following problem has been extensively studied: a bandit with K arms. Okay, so a bandit has K arms. Now, the states of the arms evolve as per Markov processes, and the states of the arm could be correlated across different states. That means the state of a particular arm may be correlated with the state of another arm. And then you, at any given time, you try an arm. That is like testing. You test an arm, and then that gives a reward and reveals its state. So then the question is, and this problem, exploitation versus exploration, has been studied in that context. Should we just exploit? Let us say we have tested a particular arm and it has given a reward. So should we just continue testing that arm, or should we just venture into arms that we haven't tested at all? Okay, so, and that problem, exploitation versus exploration, the trade-offs have been studied for multi-armed bandit problem. So there are obviously similarities, as you can tell, and but there are also important differences. So number of arms in the testing context, the population varies with time. Number of arms vary with time. If you consider individuals as arms, so the subject population varies, because maybe some individuals have died, so, or some individuals have just been born, so the subject population varies. Okay, for the bandit problem, the number of arms did not vary, it was static. And obviously number of infected nodes also change with time. And then nodes are isolated after testing positive. Okay, so the tests can't be repeated. So since the nodes are isolated after testing positive, then when a node tests positive, you send him to quarantine, you don't test him again. But for bandit problems, suppose you test and you try out an arm and it gives a reward, you can try it out again next time slot. And there is no constraint on that. But that's not true for testing an individual, especially, let us say, in fact, you can't even positive or otherwise, you can't really repeat the tests very frequently. Just consider individual. Suppose he has just tested and he has tested negative. Now, if you just ask him to test again next day, then he would not be very happy, because testing is also a disruption. So you can't really, then maybe you can actually ask him to test after a couple of weeks. So you can't repeat tests immediately because of human reaction. And but that is not the case for the bandit problem. You can test the same arm as many times as you want to. By the way, this is an important difference between control of disease amongst humans and control of another process amongst mechanized entities, the behavioral response to the disease. So for example, you need to, and all doctors and public health professionals know this, you need to elicit, you need to get cooperation from your subject populace, from your target populace, cooperation with the counters. Otherwise, the counters would fail. And therefore, and you're not going to get cooperation if the strategies are becoming extremely disruptive. And so the need to get cooperation actually imposes significant constraints on the control. That's not true for control of mechanized control of mechanized processes. All right, so exploitation versus exploration trade-off arises in testing context. For testing, this trade-off arises because there is lack of knowledge of evolving set of infected nodes. And then this trade-off also arises even when network and process model and parameters are fully known. That means you might know the rate at which a disease spreads, you might know its statistics, but you might know all the parameters of the process, all the statistical parameters. So, but still the process is not known simply because the individual states are random. Okay, so, and that is not true in the machine learning. In machine learning, oftentimes you actually try to learn the parameters of the process. So the problem arises because the parameters of the process, statistical parameters of the process are unknown. But that's not true for testing. I mean, those parameters may be unknown, but even when they are known, there are still important unknowns, and there is still the exploitation versus exploration trade-off still arises. Any questions? Okay, let's move on to the next slide. Okay, now I'm going to after laying down the problem, I'm going to summarize our contribution, and I will direct you to the paper should you be interested, and you're welcome to actually interact with me offline if you are interested. So now what we did was we designed a principled greedy testing policy towards attaining desired exploitation trade-offs. Now I'm deferring the entire formulation to our paper. Please read it there. So, and then we designed, so then if you're familiar with machine learning, you know that there is something called a message passing algorithm. That means you update the states. Okay, so let us say you may have an observation, after that you update the states. So, and the update happens through a message passing algorithm. So we designed a message passing algorithm to continually update probabilities of infection of every node based on results of each test, and posterior probability of infection given history of test observations. And you can find it in the paper below, in containing a spread through sequential learning to exploit or to explore transaction and machine learning research, appeared in 2023. Okay, any questions? Okay, now let's go on to the next one. Okay, so there are some important challenges. So in the algorithm that we developed, there are some important challenges in its deployment. Computational complexity, for example, it's the testing algorithm that we developed there, it is quite computationally challenging. Okay, and another issue in testing, that means which we engineers are not very familiar with, or maybe we are familiar with a bit if we actually if we work in industry. Maybe let us say in academia, let us say you have developed a perfect solution. However, that may still not be accepted, that may still not make its way to practice, simply because there is an inertia if that is not compatible with the solutions that have been widely deployed, then your perfect solution cannot be deployed, simply because it's not possible to throw out everything existing and start afresh. That's not usually possible. So there must be backward compatibility. You see this issue much more in medicine. So if you, let's say contact tracing is deployed extensively, which is true, it is deployed extensively. Now, if we propose a policy, even if we show that the contact tracing is significantly suboptimal, and we propose a policy and we show through, let's say, our mathematical analysis, our simulation, etc., that policy is actually that policy has significantly outperforms. Okay, overall the objective function is significantly better, but it may not still make it to practice, simply because it is very different. I mean, you have to convince the public health professionals, and public health professionals would not be easily convinced if they see that the solution that is being proposed is entirely different from what they are familiar with. So therefore, there is a case to be made for gradual evolution of existing strategies, or evolution or improvement upon existing strategies. So, in other words, can we actually develop better rather than, let's say, I mean, okay, it's definitely of great academic interest to develop an overall optimal policy, okay, which was really the goal in the previous, for our previous paper. But then, if we are thinking of deployment in practice, maybe it's a better idea to generalize, to improve upon the existing solution. So we looked at some of the improvements, some of the significant improvements that can be brought about for contact tracing. So contact tracing only exploits available knowledge. So can contact tracing, so as we said, for contact tracing, you test an individual, he tests positive, then you test his neighbors. So you're only exploiting available knowledge. But can you generalize it to explore as well? Okay, so then we proposed the following policy. It's multi-hop communication, and that has been inspired by multi-hop communication in wireless networks. If you're familiar with, well, I guess many of you would be familiar with wireless networks. So they are ad hoc wireless networks, right? So, and their multi-hop communication has been studied for a long time. An individual has a message, then he sends it to another individual, then that individual sends to another individual, etc., and the message travels multiple hops. Now we thought of multi-hop, inspired by that knowledge, we thought of multi-hop contact tracing. So let's go to the next slide, please. Thank you. So suppose, so what does contact tracing do? A node test, an individual tests positive, then then all those individuals who have been in contact with the individual who has been tested positive are tested. Okay, so that's really single hop contact. What if, but why test only single hop? Why not test two hops? That means, let's say, hypothetically speaking, if I have tested positive for a disease, then you are going to test all my immediate neighbors, those who I have been in contact with. But how about also testing those who my immediate neighbors have been in contact with? Maybe they have also imbibed their result, rather than waiting for the test results of my immediate neighbors to come and then decide who to test, whether we should, if they test positive, then let us test their neighbors. By that time, the disease may have spread through several hops. So you could actually simultaneously test my two hop neighbors. Okay, and in general, you could actually test k hop neighbors, where k is a parameter. Okay, so then, and then what are the trade-offs here? If you increase k, okay, so it will reduce overall infection count over time. Let us see if I test, test 10 hops. Yes, a node test positive, and if you test his 10 hop contacts, yes, it will increase, or it will reduce overall infection count over time. Okay, but then it also increases, maybe it does increase significant testing load. Okay, or does it? That's the question. Intuitively speaking, or naively, if you think for a minute, you think that yes, it will increase the testing load significantly. But if you think a little more, that may not be true. Why? because let us say initially you actually test a node, and you, as soon as the node tests positive, you test 10 hop neighbors. Okay, so then initially you may be testing a whole lot more, but because you are testing so aggressively, and then that is going to isolate the detected nodes, and that's going to slow down the spread of the disease. So therefore over time you may be testing a lot less. So over time, the overall testing load can also decrease with increase in K, because infection is contained faster through aggressive testing early on. However, what definitely will not decrease with increase of K is the maximum testing load. That means at a given time, the maximum number of individuals you need to test, that's going to increase with increase of K. Because here, what you're really doing, let's say you choose K equal to 10, then the testing load initially would be very high. And later on, it might actually go down significantly because the disease actually dies down. But the maximum testing load at a given time, that is definitely going to increase with increase in K. Okay. And there may be, so that's really definitely a cost. So overall testing load, maximum testing load, etc. And so that's a cost, and benefit is obviously the number of case counts, etc., is likely to decrease. So then there is a important question here: is there a diminishing return with increase of K? That means maybe you see a significant benefit if instead of just testing one hop, if you test two hops. But do you see the same benefits if instead of, if you move from K equal to 9 to K equal to 10? Maybe the benefits become marginal. Maybe the costs continue to increase significantly, but the benefits become marginal. Maybe there is a diminishing return with increase of K. Next slide, please. Okay, so then this is what we studied. Benefits case count differential with one hop testing. That means this was our metric of benefit. So suppose if you just do one hop testing, you're going to get a certain case count. Now, if you do two hop testing, take the difference. Or if you do three hop testing, take the difference. And then if the difference is significant, then the benefit is really high. And we considered the cost as the number of overall tests. So, and we found that the cost benefit trade-off shows phase transition with respect to growth rate of disease. Again, phase transition should be very familiar, is actually familiar to engineers and physicists. So we found that when the growth rate of the disease was really low, if you increase K, your benefit just increases a little bit, because there you see contact tracing, one of contact tracing is enough. So enough, the growth rate is so low, you really don't need to go beyond one hop contact tracing. So the benefit is really marginal. And if the benefit is marginal, we needn't really worry about cost. That if the benefit is marginal, why go into, even if the cost increases slightly, why go there? And then, but then when the growth rate becomes intermediate, we found that the benefit significantly increases and the overall cost actually significantly decreases. So, and then that's the second phase. In the third phase, when the growth rate is really high, we found substantial benefits, but also higher costs. So we found the cost benefit trade-offs in terms of three different phases. And we also found diminishing return. Benefit saturates with increase in K, and saturation point increases with what is the sweet spot in K. The sweet spot actually increases with increase in growth rate. And the saturation point is mostly 2 or 3 hops. In other words, what we found is if you look at 2 hops, or if you, if you're increasing the number of hops, 2 or 3 would be generally sufficient. You really don't need to do something crazy like 4 hops, 5 hops, 6 hops, etc. Okay, and growth rate actually captures. So where is the network here? In what I presented, where is the network? Well, the growth rate captures network topology. For certain networks, growth rate would be high. For other networks, growth rate would be low. And we also considered attributes that arise in practice. Cooperativity. Individuals need to cooperate. Some individuals may not want to test. We considered that. Errors in tests, false alarm, misdetection, and start time of contact tracing. That means the initial infection level. Next slide, please. And by the way, results were based on Monte Carlo simulations of a large number of topologies, and the topologies were synthetic and also obtained from actual data. And you can find these are really the two papers. The first paper was just reporting the simulations, and the second paper presented a mathematical model. Next slide, please. Okay, now I think I'm running short of time. So therefore, this would really be the last topic that I would discuss in detail, and after that I can just discuss. I'll leave the slides with you, and you can read them, and I'll just very quickly take you through the rest of our work. The reason I don't want to skip this one, group testing, is that this is one testing strategy which had actually been practically deployed in India, and India is probably one of the first countries to deploy it, and for a very specific reason. So let me just discuss the group testing strategy. And I mean, I was motivated to study this because of one of the newspaper reports that I got from India. So so here in group testing strategy, what you do is you test a group of nodes together. You collect their biological specimen and you pool them, and then you test the amount of virus in the pooled biological specimen. So if everyone is negative, then the amount of virus would be really low, so the test would return negative. So then, but the test would be positive if even a single individual is positive, because he will generate a large amount of virus, and therefore the test outcome would be positive. So then the outcome of a test is negative. When everyone is negative, outcome is positive otherwise. But when it is positive, you know that at least one or more individuals in the group who has been tested is positive. You just don't know how many, and you don't know which ones. So it is useful to rule out multiple nodes in one test after mass event. So let's actually look at the case where it has been deployed in India. So if you remember, during lockdown, lots of workers, migrant workers, went home. So they went in trains, and then the trains were heavily crowded, and the trains were full of migrant laborers. So then these now, when they disembarked on a station, there are large, they spent, the Indian trains, they take several days if you are actually traveling from one end of the country to another. For example, as a student, I used to travel from Bangalore to Calcutta, my hometown. So then I remember it was at least then that train was, I think it was 48 hours or so. So, bottom line, you spend a lot of time in the train along with a lot of individuals. So when they got off, so then there would be a significant correlation. So then group testing was actually conducted for the laborer. So let's say they get off, and then you collect, rather than testing them individually, you pool their biological samples, you test them, and if the test turns out to be negative, then you can release a lot of individuals. You don't need to quarantine them, they can go home. But if it turns out to be positive, then you have to actually monitor all the individuals. So the goal was to identify state of each node after a mass event through minimum number of tests and asymptotically vanishing probability of error. Okay, so then when we studied it analytically, we found that the state of art group testing had been studied in information theory and coding theory. But the state of the art assumes that the mostly assumed node states are independent, which is not true, which does not hold for disease. And there are lower bounds in the requisite tests in terms of entropy of the state vector. Upper bounds are available through constructive algorithms, but limited results are known for when the states of the nodes are correlated, which is the case for disease. Next slide, please. Okay, so our results in group tests. So we considered group testing, we investigated, we modeled and analyzed group testing policies for node correlation for a and we obtained the lower bound on, that means we identified in terms of entropy of the node processes, the minimum number of tests you need to get a certain detection performance. That's a lower bound. And we also give a constructive algorithm that provides an upper bound. That means you don't need more than, when you get an upper bound, that means through a constructive algorithm, then you know that you don't need more than these many tests to get the objective under consideration. So I have cited the paper. The citation is a bit dated, so it has actually appeared in Transactions on Information Theory, this paper. So, and then we considered this paper. The first paper was for a specific stochastic model for node correlation. Subsequently, we generalized it to an arbitrary stochastic model for node correlation, and then we obtained lower bounds and upper bounds. The paper has appeared in, I think the paper appeared in ISIT in 2025, and we have actually submitted it, or maybe it was in 2024, and we have submitted it for to Transactions of Information Theory. Next slide, please. Okay, so now, and then impact of human behavior on testing. Individuals may refuse to test. Now, opinion regarding testing evolves with time, space, infection level. That means I may have an infection, I may have an opinion, and I might be actually spreading that opinion. Okay, either tests are good or tests are bad. So it also, that's also opinion process is another process that evolves with time, space, and infection level. And we propose joint models for evolution of infectious diseases and opinions regarding cooperating with counters. So these are really the two papers that have appeared. Next slide, please.
Ma'am, this is the last slide.
Yeah. Oh, there is no slide. Okay. Oh, I'm sorry. Okay. All right. Then I'll just, okay. I'm sorry about that. So, okay. I'll just mention, I'll just summarize the contents of the last slide that I intended to put in, which was this vaccination. So we also studied vaccination. That means under limitations, given the number of, given limited number of vaccinations available, we modeled processes when there is vaccination. Yep. And we designed optimal vaccination strategies, and that has appeared in some public health journals. Okay, so then that is the end.
Thank you very much, Professor, for accepting our request and delivering a very interesting talk. Are there more questions from the audience? Any more questions from the audience? I hope everything is clear, Professor. So shall we conclude?
Okay, thank you very much. Thank you very much.
Yeah, thank you.
Okay.
Thank you once again, Professor.
Thank you for the opportunity, and I really apologize for not being able to make the first time.
No.
There was, some disruptions. I'm sorry about that. So I'm glad that we were able to connect, and I appreciate your flexibility. Thank you very much.
That's okay. It's our pleasure having you here. So also thank you, audience, for attending, and have a great evening. Thank you.
Okay. All right then. Okay. Bye.
Bye.